Hello everyone. I'm glad here to share you with my presentation, Mind the Bridge, New Attack Model in Hybrid Mobile Application. I am a security researcher in Octopus team. I used to focus on browsers like Edge, Chrome, and Internet Explorer. And now I am an Android application security guy. In the past, I always talk about Doomtree, Checker, V8, Blink, and so on. Now, I usually work with activity, receiver, provider, and services. There is a big range between browser and Android apps. Anyway, after a few times work, I find that maybe there is a bridge between these two areas, which called hybrid application. This is where our story begins. So, what the hybrid application is? The diagram shows the mobile app technology stacks. We can see that native apps provide the full capability, the best features, and the best overall mobile experience. Native apps are specific to a given mobile platform. HTML5 apps use standard web technologies, are easier to develop, easier to support, and can reach the widest range of devices. An HTML5 mobile app is basically a web page or a series of web pages. HTML5 apps cannot access native features on devices. Hybrid development combines the best of both the native and HTML5 worlds. Hybrid applications like native apps run on the device and are written with web technologies. Hybrid apps use common language like HTML, CSS, and JS wrapped in native code to meet device and operating system requirements. Hybrid apps run inside a native app container and leverage the device's browser engine to render the HTML and process the JavaScript locally. A web-to-native abstraction layer enables access to device capabilities that are not accessible in mobile web applications, such as the accelerometer, camera, and local storage. Let's look at it in more detail. At first, WebView is an Android view, a view that displays the web pages, a rectangle area in an Android application. It has hundreds of APIs. WebView is also a Chromium embedder. It is one of the 6 platforms support. Same compile time flags as Chrome for Android, but lots of runtime differences. Glossing over a lot of details, Chrome Desktop has lots of renders, utility processes for services, and sandbox for each render. Chrome for Android runs services in browser process instead of utility process. WebView runs services in the browser process as Chrome for Android, and it only has a single render. And before Android 9.8 or in the apps process. Even nowadays, it is the default situation for most vendors. For hybrid app, there are several bridges between HTML and native resources. Native callbacks, navigation callbacks, JavaScript interfaces, JavaScript event handler, and HTML5 APIs. The first bridge, navigation callback. Developers have the option of controlling navigation within WebView. Whenever there is a navigation on a WebView, the developer can intercept this or get notification. Like, should override the URL loading, on page finished, on page started, and should intercept request. Navigation callbacks are invoked during the life cycle of navigation. These diagrams show a part of timeline of what happens in the navigation. I delete the initialization and some other steps to make it simple. It starts in the yellow, means browser model. In Android, also means UI thread. In blue, we have network service, and in green, we have render thread. First, we call a function called begin navigation. The next step is to hop over to the network service, which will actually start the URL request. Once we hear back the response, we jump back to the browser thread and choose a render thread, which will show the page. Next, after that, is to tell the render to commit the new navigation and send back an ACK to browser. At this point, the navigation is basically finished, but nothing is shown on the page yet. Next step is read the response body and render it into a web page. Once that's done, it will let the browser know with another message and say, OK, stop load. Should the override URL loading is called at the beginning in the function begin navigation. Should intercept request is called when the network service start URL request. On page started is called after begin navigation. This callback performs different after version 72, but I will not talk about this today. On page finished is called after page render is in render thread. The WebView API is also allow inserting Java object into WebViews using the JavascriptInterface method. It registers a Java object with a specific WebView instance. JavaScript loaded in the WebView can have access to applications' internal Java code, giving web code the ability to interact more tightly with an app, and in some cases get access to system resources. It is a quite convenient way to exchange data. At first, application create a Java object, add this object to WebView with API add JavaScript interface. WebView will create a type of object named GenJavaBound which is a reflection in the browser model, so the WebView can interact with the Android code by this object through JNI. Render model also needs an object to interfere with V8 engine, which called GenJavaBridge. This kind of object will be bound with an empty V8 object. This empty V8 object will be injected into the V8 global environments, so the JavaScript code running in a render thread can access the Java object with the supplied name. The third bridge, JS Event Handler. The WebView API allows developer to handle the alert, promote, and confirm JavaScript events by register the onJS alert, onJS promote, and onJS confirm Java callback methods. Whenever the JavaScript side call any of these event methods, their respectively handler will be called if it is override. The developer is free to implement any logic in this event handler. And the fourth bridge, HTML5 API. The release of HTML5 has brought in a set of APIs that can give web applications the ability to access device hardware via JavaScript. For example, geolocation and getUserMedia, which enable access to GPS and to media devices such as camera and microphone. Developer needs to make use of onGeolocation show promote and onPermission request to grant or deny permission to the requests. These bridges provide our powerful feature but also present security risks. When JavaScript interface is invoked, there are at least two OP codes in JavaScript engine. First, getMethod. As we said before, the object we see from JavaScript is an empty V8 object, so render will transfer has method to browser model and invoke Java built-in function class.getMethod through JNI. Certainly, there will be a catch in GenJavaBound object. Like you think, the return value is also template, just used to tell the JavaScript code, yes, there is a function. Second, invoke method. It works like getMethod. It uses reflection to invoke the target method and reflect the return value. And this is how CVE 2012-6336 works. The JNI invoke class.getMethods will return all the methods this Java object has, without any filters. Also, the native built-in runtime. Attacker can get remote code execution on WebView with the exploit. So Google added an annotation JavascriptInterface to avoid this situation. getMethod will first validate whether the return method has the annotation JavascriptInterface. All Java objects injected by API add JavascriptInterface will have this restriction. But those who do not inject it through a JavaScript interface will not. It is YCVE 2014 1939 and CVE 2014 6224 occurs. Another well-known issue is ape clone attack. If WebView sets this 3 function true or default value, attacker can steal user's private file with a malicious local file. With the help of setAllowFileAccess, WebView can load a local page. With setAllowFileAccess from URL, this local page could access any private file with app's permission. After get private files from target app, attacker can totally clone a victim account in 20,000 miles away, and victim may not get aware. Some HTML5 API can also be abused. For example, geolocation. If the value set geolocation enable is true, and the callback on geolocation permission show promote do not ask for user authorization, attacker can use the HTML5 API navigator.getGeolocation.getCurrentPosition to get user geolocation remotely without any notification. However, the most common bridge problem is JavaScript interface abuse. Some app manufacturers prefer to implement a sensitive filter in JavaScript interface. For example, getUserToken, access local file, install other apps, and other. Inject the supplied Java object into WebView. The object is injected into all frames of web page, including all the iframes, using the supplied name. This allows the Java object's methods to be accessed from JavaScript. The Android developer document has warning. There is no way to tell the calling frame's origin from the app side, so the app must not assume that the caller is trustworthy unless the app can guarantee that no third-party content is ever loaded into WebView. But in real world, this important tips is not always fulfilled. Applications usually need to load unexpected web page for some business reason. In this case, to use the JavaScript interface safely, manufacturer would perform app-specific security checks to ensure the JavaScript interface can only be invoked by specific URLs. There are many fantastic designations, but no matter what sec checks are, they have to rely on the URL get from WebView. There are 2 widely used mechanisms, Lifecycle-based access control and real-time access control. Lifecycle-based access control gets the URL from the navigation, callbacks like should override URL loading, and onPage started. These callbacks will be invoked during the life cycle of navigation from different models, as we stated before. Application will get URL from these callbacks and save as current URL when there is a JS bridge call. Application will treat this call as from that URL. This is a demo code. Application manufacturer get value from should override URL loading and save it to a variable current host. When the JavaScript interface get token invoked, it will check whether the current host is authorization. This mechanism is proved to be unsafe. Attacker can use time delay attack to bypass this access control. Attacker first trigger navigation to change the variable current URL. After that, jailbreak call from the evil web app will treat us from the new trusted web app. In the diagram, you can see where and when it happened. Either should override URL loading or onPage started is invoked before old render page unloaded. And as long as there is a new navigation, the access control URL will be replaced by the new one. And there is a time window between callbacks and old render unloaded. Therefore, any old render into JavaScript interface invoking in this window will be treated as from new render. This is a real-world exploit. Location will trigger navigation and fix the lifecycle callback. Those set the wrong current URL. With the help of set timeout, getToken will be executed after navigation. Thus, the access control will be bypassed. So nowadays, more and more applications use real-time access control. They do not get URL from callbacks, but use WebView.getUrl in main thread when JavaScript interface is invoked. We know that JavaScript interacts with Java object on a private background thread of WebView. So this solution uses a runnable to maintain thread safety. With the help of real-time access control, the traditional time delay attack will not work, because WebView.getUrl may not affected by JavaScript code in most cases. So next, I will show you the new threaten. A totally new attack model will affect real-time access control as well. Let's dig into the function WebView.getUrl. It's not that simple as we think before. Actually, the function can return two kinds of value, pending entry and last committed entry. Generally to say, when the function is called after a browser-initiated navigation, it will return pending entry. When this function is called after a render-initiated navigation, it returns last committed entry. It seems interesting that during different types of navigation, WebView.getUrl will return different value. There are two types of navigation, browser-initiated navigation and render-initiated navigation. Render-initiated navigation starts from render process. This would be like click a link, use a form, or just a piece of script. It is less trustworthy because bad web pages can try to send you bad places, but not internal pages. We also have browser-initiated navigations stem from URL, omnibox, bookmarks, context menus, and other UI interaction navigation. This is a timeline of browser-initiated navigation as we've seen before. Pending entry will be set at the beginning of navigation in browser model, and the last committed entry is set after the render page is committed. This is a timeline of render-initiated navigation. The only difference in the navigation form is that it starts to render and certainly will not set pending entry. In hybrid app, render initiated navigation can be triggered by JavaScript code, so it is untrusted and needs lots of verification to ensure the context is no tamping. Browser-initiated navigation is triggered by load URL. Most of the time, it is trustful. Browser-initiated navigation will set pending entry at the beginning of navigation and return it during getUrl, while render-initiated navigation not. Let's summarize. For browser-initiated navigation, getUrl will return the new URL, even before the old render model unloaded. For render-initiated navigation, it will return old render URL before the new one is committed. It seems okay for a general desktop Chromium-based browser. These two types of navigation is strictly compartmentalized in general desktop browser, but in some other cases like WebView in Android, things get different. WebView has some specific mechanism allow JavaScript code interact with native. This means JavaScript code in WebView is more powerful than in general browser, and some assumption for browser is no longer suitable for hybrid app. Let's get back to the getUrl. As it said in the comment, the pending entry is set to return for new browser-initiated navigation. Most render-initiated navigations should not show the pending entry to prevent URL spoofing attacks. In hybrid app, browser-initiated navigation can also be invoked by render model with bridges. In this case, the code will treat the JavaScript code-triggered navigation as a pure browser-initiated navigation, and return pending entry, which may not be the current URL. In another word, if developers do not know the difference between browser-initiated navigation and render-initiated navigation, there will be a vulnerability, and there will our attack. This new attack called Navigation Confused Vulnerability. We have found 3 vulnerability models in real world. First one, direct navigation confused vulnerability. If application expose WebView.load URL through JavascriptInterface directly, an evil JavaScript code could use this JavaScript interface to invoke and browser-initiated navigation from render model. Therefore, the URL get from WebView.getUrl is not trustful. It will return pending entry. Any validation based on this value will be bypassed. In real world, applications may not implement logic that simple, but they prefer to do like this. For some secrecy agreement, I could not tell what the apps are, so let's just focus on the code itself. The interface check login accepts a parameter destination URL, and if the current login status is fulfilled, it will load destination URL with WebView.load URL. Therefore, untrusted JavaScript can trigger a trustful browser-initiated navigation. Attacker call bridge check login to invoke WebView.load URL. It is a browser-initiated navigation. Browser-initiated navigation will set pending entry. Then attacker call getToken. This bridge get URL from API WebView.getUrl. During browser-initiated navigation, WebView.getUrl will return pending entry, the fake URL. This exploit looks like a normal time delay attack. Use setTimeout to postpone getToken. Use jsbridge.checkLogin to trigger a browser-initiated navigation. And the WebView.getUrl in jsbridge.getToken will return pending entry, google.com, a URL in whitelist, and bypass the verification. Second model, redirect navigation confused vulnerability. If application calls WebView.load URL in a navigation callbacks, it will convert render-initiated navigation into browser-initiated navigation. Thus, evil JavaScript code could use these callbacks to trigger a browser-initiated navigation from render model. It is a real bad idea. Apps should never ever do this. But it is extremely common, thanks to the really widely copy-paste online. You can find lots of examples on Stack Overflow. In real world, we find two typical misuse. If the redirect URL matched a specific partner, apps think it is a protocol message, and will extract another URL inside it and load this one. In the demo code, if request URL match scheme protocol, it will be treated as a protocol message and get parameter fallback URL as a new target. Attacker can use location to trigger a render-initiated navigation. A render-initiated navigation will trigger should override URL loading. A specific URL in should override URL loading will invoke WebView.getUrl. The render-initiated navigation is converted into a browser-initiated navigation. Then, attacker call getToken. This bridge get URL from API WebView.getUrl. WebView.getUrl will return pending entry, and this is the wrong value. The exploit looks like this. The location is a specific URL start with scheme protocol. Should override URL loading will extract parameter fallback URL and will trigger another browser-initiated navigation. The WebView.getUrl in js.getToken will return the pending entry, which is google.com, a URL in whitelist, and bypass the verification. Another common misuse like this. When the orange redirect URL is not matched a specific partner. For example, in this code, if the redirect URL do not start with recharge.com, Hybird app will think it is a illegal URL and would be redirected to a hard-coded legal URL, which usually in whitelist. Attacker can write exploit like before. Third one, shared navigation confused vulnerability. Compared to the last two models, this one is more puzzled. If the launch mode of the activity who holding WebView is single task or single instance, the WebView could be reused. A specific deep link could launch this activity and load page in WebView. If you invoke deep link twice, two virus patches would display, but there will be only one WebView object. Therefore, our deep link could be converted into a browser-initiated navigation on a same WebView object. It has the same effect as last two models. Maybe a diagram will be clearly. If a WebView's launch mode is single task, there will be only one WebView object, and any deep link will be converted to load URL in this single one. In the diagram is A.com and B.com. Thus, we find another way to invoke browser-initiated navigation from random model. In the diagram, you can see the C.com is also loaded in the WebView. There are two ways to attack shared navigation confused vulnerability. If WebView can trigger deep link itself, it's quite simple. Attacker use location to trigger a deep link, and the launch mode of the WebView is single task, and this deep link will be converted into a browser-initiated navigation, and the WebView will be reused, and the WebView URL and a deep link will be converted into a browser-initiated navigation and set the URL in deep link to pending entry. During access control, WebView.getUrl will return the pending entry. Then, attacker call getToken. This bridge getUrl from WebView.getUrl, and certainly, this is a fake URL. We can do exploit like this, just like before. Location will trigger a deep link and launch WebView. Due to the single task launch mode, WebView will be reused, and it will launch a browser-initiated navigation in the current WebView and affected the return value of WebView.getUrl. If target WebView cannot trigger deep link, we need a third-party browser help. Attacker needs to trigger deep link twice in sequences. First, deep link load an attacker side to get token, and the second deep link load an trustful URL to bypass verification. Use JS event visibility change to do this automatically. This event will fire when the content of its tab have become visible or have been hidden. This exploit works in some third-party browser like Quark. The function attack will load attacker.site in target WebView, and due to the deep link, the third-party browser is hid, and the event visibility change will be fired. And after a short delay, the event handler will load google.com through deep link in the same WebView. And the verification will be passed as before. These are the vulnerability models we find so far, and I believe it is just a tip of iceberg. Next, I will show you how to mitigate this kind of vulnerability. Because for some business reason, the web page that needs to be loaded is not easy to be modified. So, most of the time, we could only enforce our application. To help you find these vulnerabilities, we developed a novel tool that can vet Android apps automatically. It is a path search tool based on Android Guard. It has 3 simple logical to find these 3 vulnerability models. It finds a path from JavascriptInterface to WebView.loadURL, and find a path from navigation callbacks to WebView.loadURL, and try to find a single task launch mode activity holding WebView. Due to the problem is root from WebView native code, Android developers actually have less to do. They can only try to avoid the vulnerability models I noticed before. But it is not enough. As I said, this 3 model is just tips of iceberg. So, we come up with Richinterface, an enforcement in a deeper side. We change the way WebView invoke Java objects. This diagram shows how Richinterface worked. Let's remember how JavascriptInterface worked. A V8 object in JS Engine, a GenJava bridge object in render, and a GenJava bound object in browser, and finally, the Java object. We noticed that in browser model, we can clearly know where this invoke comes from. But this important information was banned during JNI call. Richinterface will do another explicit JNI call, transfer the URL, so the verification can get a correct data. The only change application needs is add a setURL JavaScript interface in the Java object to receive the message. The time window between setURL and the actual JavaScript interface call is small enough to be ignored. This is a demo using Richinterface. We can see it is quite simple. The only thing you need to do is add a JavaScript interface named setURL, and this bridge will be called automatically when the bridge getToken is called. Before Richinterface, application cannot get the correct URL from WebView. Attacker can use navigation confused vulnerability to bypass the whitelist checker. After Richinterface, application can get URL from JavaScript interface directly. Any attack try to abuse URL could not work. What's more, other mitigations like NoFrank or Jekyll is also worked. Thanks for their awesome help. There are two lessons we learned. First, document will lead us, whether we have read the document before we use the API. Both app clone attack and navigation confused vulnerability are caused by inaccurate reading of the document and inadequate understanding. Second, for cross-platform framework, some preconditions may not meet in every platform. And this is all. Thanks to all my team matter, and thank you for your attention.